Okay, so hello everybody. Welcome to the One World Mathematical Physics seminar of the IAMP. It's a great pleasure to introduce today's speaker, Jian Ding from Peking University, and the title of today's talk is Repeated Emergence of the Fourth-Order Exponent. So Jian, we're very much looking forward for your talk.
Thanks for the invitation, and thanks for the introduction. It's just by the title of my talk, I will explain the emergence of the fourth-order exponent in a few seemingly unrelated probabilistic models. While I will review related progress on these topics, the two papers that feature the emergence of fourth-third is with Subhajit Goswami and with Mateo Wirth, both of whom are my former graduate students. Also, since I will discuss the intersection of a few different models, when I discuss each of them, I will not be comprehensive. I will just focus on closely related progress for these models. Okay. Also, feel free to interrupt me anytime during the talk. So here is an outline of the talk. First, I will present the emergence of the fourth-third exponent in random metric of Liouville quantum gravity, and also in the correlation length of the two-dimensional random field Ising model. Then I will explain that despite the fact the appearance of fourth-third in these two models somewhat surprising even to physicists in this community, this fourth-third has actually been hinted in a work by Leighton-Shor that went back to 80s when they work on random planar matching. I will explain this connection, and toward the end of my talk, I will sketch the back on the envelope calculation, which hopefully would explain why the fourth-third exponents would emerge in all these models. Okay, so let's start with Liouville quantum gravity. Liouville quantum gravity is a canonical random surface model. It was introduced by Polyakov in 1980s in the context of string theory. Basically, the idea is we want to define a two-dimensional random Riemannian manifold in a certain canonical way. Another way to define a random surface is to look at discrete random planar maps and then take scaling limits. And LQG is the second natural way to define a canonical random surface model. So these two are naturally connected to each other, and they are also deeply connected to conformal field theory. In the last couple of decades, random planar maps and LQG have been extensively studied as cornerstones of random planar geometry. Now let's be a bit more precise about how to define LQG. Fix a parameter gamma between 0 and 2, and also take U as an open domain in the complex plane. Then formally, a gamma LQG surface is the surface with the Riemannian metric e to the gamma h times the metric tensor for the Euclidean metric. Here, H is a variant of the Gaussian free field on the domain U. Its precise definition is not so important for this talk. Roughly speaking, it is a canonical random height function in 2 dimensions. A simulation is illustrated in the picture on the top left corner. But I do want to point out that Gaussian free field is not well-defined pointwise. Intuitively, it means that this random surface is too rough. It is only well-defined as a distribution. As a result, the aforementioned metric tensor does not really make literal sense On this topic, much of the effort is dedicated to giving a rigorous meaning to it. From the collective efforts of the community initiated by Kahan, the area measure perspective of LQG has been fairly well understood. As you may be able to see from the illustration on the bottom left, the LQG area measure is an interesting random fractal measure whose support has dimensions strictly less than 2. But today, I will not discuss much about it because the focus is on the random distance of LQG. Now, how should we make sense of the distance on the LQG surface? Actually, this is very similar to how we make sense of LQG area, or in a way, it's similar. This is using the standard approach, which makes sense of many objects that is related to two-dimensional Gaussian free field. That is, we use a regularization procedure. Even though GFF itself is too rough to make sense as a function, but we can try to approximate it by a smooth Gaussian random field. For instance, we can approximate GFF by a circle average process. That is to say, we define H epsilon Z, the circle average value, as the average of the GFF on the circle centered at a Z with radius epsilon. This is a well-defined Gaussian field, and as a result, we can use this to assign a random length to each nice curve by integrating the exponential of gamma times this circle average value against the big measure of the curve. Now, once every curve has a random length, the distance between 2 points is naturally defined as the shortest length between, it's the length of the shortest path between these 2 points. But this is not yet over because H epsilon, this is still an approximation of the GFF. We still need to take a limit as epsilon goes to 0. This is the hardest step in this whole program. Because we wish to show as epsilon goes to 0, this distance we define as d epsilon above has a limit, has a well-defined limit. This is not so easy because compared to the LQG area measure, for the area measure, one can do fairly explicit computations, and also there is a nice martingale structure from which it's not too hard to show there is a convergence for the area measure. Well, when I say not too hard, it still requires a lot of effort from the community, and this one sentence encapsulates many papers, many important papers. But compared to the area measure, the distance is still, I think it's fair to say that it is much harder, for the reason that in this definition, there is a global optimization when we take the shortest path. And as a result, explicit computation is very difficult if possible at all. And as a result, to prove the convergence of the distance, we use a more conceptual approach, which is also somewhat standard because we first show the tightness, then this guarantees the existence of the limit. This was proved by Dubidad, Donap, Falconet, and myself. Once we know the limit exists, then a standard approach is to formulate a bunch of axioms and show that every limit that satisfies these axioms must have the symbol. And this is indeed the case, and it was proved by Yunguin and Jason Miller. And altogether, this gave a well-defined LQG metric for all gamma between 0 and 2. This is the so-called subcritical regime. We can also do the same thing in the critical and the supercritical regime. This was shown in a couple of recent works with the Yun-Guang. Similarly, to the subcritical regime, we know in this case, the normalized metric also converges to a limit. Although I do want to point out there is a bit difference between these regimes. Crucially, in the subcritical and the critical regime, the limiting metric induces an Euclidean topology, but in the supercritical regime, the metric does not induce a Euclidean topology. In fact, the supercritical metric is very wild. For instance, it has many singularities from whose distance to any other point is infinite. So it's actually drastically different from the Euclidean metric. Okay, one very natural quantity of a metric is its Hausdorff dimension, and for this we only have very partial understanding about the LQG metric. We can show that there exists a number that depends on gamma, which can describe the dimension of this metric. In fact, this number was defined even before the metric was constructed, because this number can arise from various discrete approximations of LQG distance. For instance, if we look at a corresponding random planar maps, this number describes the exponent of the volume growth for a graph distance metric ball in this planar map. Once the LQG metric was constructed, it was indeed shown that this is the Hausdorff dimension of the metric. A important problem is to compute the exact value of d sub gamma. But for this, we only have fairly good lower and upper bounds, but we do not know the exact value of d sub gamma, except for the very special case of pure gravity, which essentially is a single case for gamma equal to square root 8 over 3, at which certain magic occurs, and one can get the exact number for the dimension. The promise for third exponent arrives in the joint work with Subhajit Goswami, where we obtained a lower bound on this dimension when gamma is very small. That is when the metric is not distorted too much from the Euclidean metric. Our proof is based on a multi-scale analysis. I mean, I'm not going to tell you any detail about this, although at the end of my talk, I will sketch a computation that is similar in spirit in the context of a different model. I do want to say that this bound was fairly surprising because it contradicts with the well-known and then well-believed prediction by Wattabiki in 1993. In fact, once the prediction of Wattabiki was known to be not correct, people tried to come up with reasonable new guesses about this formula, but so far, I don't think there is a consensus on even the level of physics rigor on what the formula of d gamma should look like. I would say it is a major open problem to compute the dimension, and it would be great progress to even compute d sub gamma for yet another non-trivial value of gamma. Okay. So now let's move to the second topic, which is the random field Ising model. Physically, the Ising model is a model for magnetization. Mathematically, let's define it a bit more precisely. So we can consider the lattice as nearest neighbor graph, and we can say consider a box in the lattice. Then we want to consider the configuration, which assigns each vertex in the box either a plus or minus spin. We also pose some boundary conditions as shown in the picture. Of course, we can pose arbitrary boundary conditions, but for the purpose of this talk, it would be enough to just consider O plus boundary condition. Once we have all these definitions, we can define the Hamiltonian for a configuration. The Hamiltonian is with respect to the boundary condition, by the way. It's defined as follows. It's shown in the method display in the slides. In the definition, there are two sums. The first sum incorporates the spin interaction across neighboring pairs, and the second sum incorporates the interaction between the spin and the boundary condition. The plus minus sign in front of the second sum corresponds to the plus and minus boundary condition. Then for any non-negative temperature T, we can define the Ising measure, which assigns the probability to each configuration that is proportional to exponential of -1/T times the Hamiltonian. Perhaps you have noticed that this minus sign in the definition of the Hamiltonian and the minus sign in the definition of the Ising measure, they should cancel each other mathematically. That's right. We keep these minus signs just to follow the convention in physics. Also from this definition, it is clear that the Ising measure favors configurations that have more agreeing neighboring pairs. And also the lower the temperature is, the stronger this effect is. A very interesting question is whether such local spin interaction leads to long range order. Physically, long range order means magnetization, and mathematically, we can measure long range order by the boundary influence, which is just the spin average at the origin with the plus boundary condition. Here, the bracket means taking expectation with respect to the Ising measure. And then we say that the long range order exists if the boundary influence stays above a positive constant as the sides of the box goes to infinite. As I said earlier, physically this implies magnetization. In his thesis in 1925, Ising proved that in one dimension there is no long range order for any positive temperature. And in the important work of Peirce in 30s, it was shown that for 2 dimensions and above, long range order exists at low temperatures, but not at high temperature. Peirce's work is important not only for the reason that he introduced a standard method for proving phase transitions in statistical physics models that has been widely applied in later study, but also it shows that despite being so simply defined, the Ising model enjoys a very intriguing phase transition. This, together with the critical phenomenon, has attracted extensive attention from various communities to the study of the Ising model. I think in statistical physics, Ising model is probably one of the very few most studied models. There has been a lot of progresses on the Ising model from the mathematical perspectives. I think in the audience there are at least a few experts that has done just remarkable work on this topic. But today I will only focus on one facet of the Ising model, which is whether disorder would, or how disorder would affect the long range order. Okay, so now let me define the model, the random field Ising model. For simplicity, let's consider HV as IID standard normal variables indexed on the vertex set of the lattice. Then this is the disorder. Then we can define the random field Ising model Hamiltonian with with the strength epsilon as follows. The Hamiltonian is the original Ising model Hamiltonian plus another term, that is the term in blue. The minus sign here again inherits from the minus sign that comes from the physics convention. This blue sum incorporates the interaction of the Ising spin with the external field. Then similarly, at any non-negative temperature, one can define the random field Ising measure in the similar way, except we replace the original Ising Hamiltonian by the Hamiltonian for the random field Ising model. Maybe I should point out that this measure itself is a random variable which depends on the disorder. Also, at 0 temperature, this measure is supported on the ground state, that is the minimizer of the Hamiltonian, and the ground state is unique because Gaussian is a continuous distribution, and with the probability 1, we do not have 2 configurations that have the same Hamiltonian. Interestingly, without the disorder, the ground state is trivial, basically, because with plus boundary condition, the ground state is all plus. With the minus boundary condition, the ground state is it's all minus. But with the presence of disorder, even the ground state exhibits very interesting and highly non-trivial structure. In fact, for many of the questions, the study of the ground state almost encapsulates most of the mathematical difficulties. Again, we are interested in the long-range order, and as a result, we're interested in the boundary influence. Since there is another layer of randomness that comes from the disorder, we may just take expectation over the disorder to define the boundary influence for the random field Ising model. So the main question is, how does the random field affect the long-range order? Or in other words, what is the limiting behavior for this boundary influence? It is not so hard to imagine that if epsilon is large, that is, if the disorder is strong, pretty much the Ising spin would like to be aligned with the disorder, and as a result, the long-range order will be destroyed. And in fact, this was proved rigorously in a series of mathematical works. The much harder case is when epsilon is small, that is when the disorder is weak. For this, Imre and Amar made the following predictions in 70s. For 3 dimensions and above, they say that long-range order exists at low temperatures, and for 2 dimensions, there is no long-range order at any temperature. That is, the boundary influence vanishes in this case. Here is a very rough underlying intuition of Imre and Amar. If you look at the Gaussian volume, that is the sum of the Gaussian disorder in a box, typically the order is just the standard deviation, which is n to the power of d over 2. And the boundary effect, if we think about it, should be measured by the size of the boundary, which is n to the power of d minus 1. So when d is greater or equal to 3, the boundary effect is much larger than the Gaussian volume, and as a result, long-range order persists. But when d is equal to 2, these two become comparable. And even though the Gaussian volume comes with the small factor of epsilon, Imre and Amar still predicted that eventually the disorder would win and destroy the destroy the long-range order. I think it's fair to say that this intuition is fairly rough, and this is partly why mathematically it has been a challenge to prove these results rigorously. In what follows, I will review progress on the mathematical side, but we'll only focus on the case when the dimension is 2, because this is what is related to the for third exponent. In a celebrated work of Ising and Liouville in 1990, they proved that indeed there is no long-range order. Their proof employed some ergodic theory type of argument, and as a result, they didn't get a quantitative rate of decay. It has remained a challenge for quite a while, and there has been a debate. There has been some debate among physicists whether the decay rate should be always exponential, or there's some sort of BKT type of transition, meaning the decay rate transits from polynomial to exponential as epsilon varies. There has been no mathematical progress for a few decades until very recently. Chatterjee proved a 1 over root log n upper bound, and then Eisman Pellet proved a polynomial upper bound by enhancing and streamlining the argument in Eisman and Liouville. The power on the polynomial upper bound, the gamma here, from Eisman Pellet's work is fairly small for small epsilon. In fact, if one can prove a polynomial decay with the power strictly larger than 1, then by standard arguments, one can enhance this to exponential decay. And this was finally proved a couple of years ago. It was first proved by Jian and myself at 0 temperature. And a key novelty in this work is an application of a work of Eisman and Burchard in 90s on regularity of percolation systems. I will not explain what is this and why it is related to the random field Ising model in this talk, because this is not the main focus for today. And later, this was proved for positive temperatures by 2 concurrent works, one by Jian and myself, another by Eisman, Herrera, and Pellet. Both works used this observation of applying Eisman Burchard at 0 temperature, but addressed additional challenges coming from positive temperatures in different ways. So far, all these discussions are for small epsilon, but fixed epsilon, and we look at the limits when n goes to infinite. Another natural question is, what happens if also epsilon goes to 0? And this leads to the question of the correlation length. So there are a couple of ways, or maybe even a few ways to define correlation length. Perhaps one natural way, well, not perhaps, one natural way to define the correlation length, since we have a exponential decay, is by the inverse for the rate of the exponential decay. This we don't quite know how to analyze, but another notion of correlation length is as epsilon goes to 0, what is the minimal size of box to see the influence of the random field? Because if the size of the box is fixed, as epsilon goes to 0, of course, in the limits, that's as if there's no disorder. But if the size of the box grows in a certain rate as epsilon goes to 0, then at some critical scaling, the influence from the boundary condition and the influence from the disorder become comparable. And this critical scaling is another natural notion of correlation length. And this is what we can say something about. So in a joint work with Mateo Wirth, we proved that this correlation length scales as e to the epsilon minus 4/3 at 0 temperature. And also this upper bound applies for all positive temperatures. I do want to say that this emergence of 4/3 exponent is unexpected to physicists. Despite an extensive study using either simulations or non-rigorous methods, there is no consensus on this on the scaling of correlation length among physicists, even at 0 temperature. Predictions include Gaussian scaling and exponential scaling, but I did not find I do not find in the literature the fourth exponent for this correlation length. Also later in the work of Zhang and myself, we proved that the lower bound also holds at the low temperature. Although I do want to emphasize that here by low temperature, I mean very low temperature. We do not have a result when T is near Tc. You may wonder what happens at high temperature. In a joint work with Jian Song and Rongfeng Sang, we proved a general inequality about the Ising model, which in particular says that the boundary influence can only decrease with disorder. And as a result, that says at high temperature, we always have exponential decay for the long range order. So the question of correlation length doesn't quite apply. Also, let me point out here, by high temperature, I mean when T is above Tc, which is the critical temperature without disorder. We do not know the detailed phase transition for the correlation length. Especially, we don't know the possible critical phenomena. It is possible that if the size of the box grows in epsilon in some carefully chosen manner, then maybe at some critical temperature that is different from the original Tc, something interesting happens that at this moment is, at least seems to us to be out of reach. Now, I do want to explain, I want to come back to the main theme of the talk, which is about the fourth exponent. I want to describe that this fourth exponent was already hinted in a work by Leighton-Shor in 1989 when they study random planar matching. This is actually a bit interesting because we know of Leighton-Shor's work vaguely, but we didn't manage to draw a connection until very recently when we try to improve Leighton-Shor's work in matching. And by the way, we didn't succeed. In what follows, I would like to tell you the story.
Jian, can I ask a question?
Sure.
Is it possible to make more precise what do you mean by see the influence from the random field?
By what?
So in this question, you ask what is the minimal size when you see influence from the random field?
Right.
What do you precisely mean by you see influence from the random field?
Sure. If there is no influence from the random field, for instance, if it's at a 0 temperature, then the origin would just agree with the boundary with probability 1, right?
Mm-hmm. Mm-hmm.
When you start seeing the influence, it means, okay, the probability for the origin to be plus with the plus boundary condition started being, so drops below, say, a half or any number that is strictly less than 1.
Okay.
Does that make sense?
Yes.
Okay. Great. So now we come, yeah. Do you have something else to say?
Is this specific observable that is something you treat here? I mean, it's just, was it just an example, or you really look at this particular?
We really look at this, yes.
Okay, thank you.
Okay. Okay, so this connection is actually via yet another object, which is the random gradient lattice animal. So now let me explain first why random field Ising model is related to the gradient lattice animal. And then I will explain why the random matching is related to gradient lattice animal. And after all of this, I believe then we see there's a connection between random field Ising and the matching, okay? Again, let's use the 0 temperature as an example. So it's not hard to see that the disorder has influence if with a positive probability, ground state at origin disagrees with the boundary condition. Actually, this is what we just discussed in answering Harold's question. Then if that happens, the sign cluster of the origin should satisfy that the epsilon times the Gaussian volume should be larger than the size of the boundary. Because if that's not the case, we can then flip the signs in S, and this would further decrease the Hamiltonian and contradicting with the ground state assumption. This is not very hard, but if you cannot see it immediately in your head, it's not a big problem either. Trust me for this one. Now, in light of this, let's define the greedy lattice animal, which is the, we look at the maximum over all connected subsets that contains the origin, and we look at the value of the Gaussian volume normalized by the boundary sides of the set. Here, the lattice animal just means a connected set in the lattice. This is just a terminology. Maybe it's because that a connected set in the lattice looks like an animal if you use the imagination. And the greedy here means we take a maximum. And then from the discussions above, we see that the upper bound on the greedy lattice animal gives a lower bound on the correlation length at 0 temperature. This is actually precise, exactly because of for this sign cluster has to satisfy that the Gaussian volume beats the boundary sides. And it is then just natural to imagine that the growth rate for the greedy lattice animal as n goes to infinite should be responsible for the growth rate of the correlation length for random field Ising model. And it is indeed the case for the greedy lattice animal. It grows like a power of log, and the power is 3/4. And this upper bound was actually hinted in Leighton-Shor in 1989, and this was further elaborated in Talagrand's book in 2014, when he presented a unified proofs for various matching theorems using the majorized measure theory he established. We didn't quite know this, so we also presented our proof by a certain multi-scale analysis argument, which combines a geometric intuition that I will explain toward the end of my talk. Okay, so this is the connection between random field Ising and the greedy lattice animal. Now let me explain why matching also kicks into this picture. Let me first explain what is matching. Suppose we have ID uniform points in a 2-dimensional box, and in this box we have like n square lattice points too. We want to match the uniform points to the lattice points in a certain optimal way. Usually we want the transportation distance to be minimized in a certain sense. This is an example of optimal transport theory, and this also has wide applications in statistics and algorithms. In fact, the original motivation for Leighton-Shor to study this is to analyze the behavior of a certain beam packing algorithm with random inputs. Beam packing problem is a classic combinatorial optimization problem that is known to be hard to solve. Basically, you can imagine there are boards whose mass is between 0 and 1, and we have beams which can hold mass that is at most. We have beams which can hold total mass that is at the most 1. And given a collection of boards, we ask how many beams. What is the minimum number of beams we need in order to hold all these boards? This simply sounding question turned out to be very hard to solve, and it is in analyzing some sort of online algorithm with random inputs. Leighton-Shor studied this matching problem. But perhaps the most classic result on this topic is due to a Agitai, Komlos, and Trusnadi, who proved that if we want to minimize the average transportation distance, the best one can do is order of root log n. And the result of Leighton-Shor says that if instead of minimizing the average transportation distance, one wants to minimize the maximum transportation distance, then the best one can do is log n to the power of 3/4. And there's actually a very interesting open problem along this line posed by Talagrand, who called this as a ultimate conjecture. Basically, the AKT controls the L1 norm and the Leighton-Shor controls the L infinite norm. Talagrand wants to find a matching that controls the optimal profile for the transportation distances, which in particular would simultaneously achieve this L1 and L infinite bounds. It is during the investigation of this question we discovered the connection between random field Ising and the matching, but we didn't manage to make progress on this conjecture for matching. Now let me explain a bit more carefully why matching is related to the Grady lattice animal. Before doing so, let me remind you what is a Hall's criterion, because this is the key. The Hall's marriage lemma says the following. In the slides, I presented in terms of matching points, but verbally we can also think of there are n jobs and also there are n workers. And each worker can perform certain subset of the jobs. We want to assign one job to each worker so that everyone is doing what one is able to do. This is a very natural setup. It is easy to see that for any subset of the workers, in order for the existence of such an assignment, the number for the union of the jobs this subset of workers can do has to be at least the number of workers in this subset. Right? Otherwise, it's impossible. The key point of Hall's marriage lemma is that this is also sufficient. If for every subset of workers, the number of jobs they can do altogether is great equal to the number of workers in this subset, then there exists a valid assignment. Okay. In light of this, if we want to use this to say something about to control the maximal transportation distance in matching, a natural choice for this AI, which is, well, AI just means now the number of jobs, the set of jobs a worker can do, but in our language should be points. The natural choice for AI would be all random points in a ball of radius r centered at the lattice point y sub I, right? Because we want to match y sub I to some point in this ball. If we can succeed, then the maximum transportation distance is bounded by r. Now, the crux of Leighton-Shor is to verify Hall's condition holds for r equal to log n to the power of 3/4. If we think a bit, we can see that the hardest case to check, or the crux of this, is when I is the set of lattice points in a simply connected subset of r to the power of R2. Also, one can be convinced that how can we compute the number of random points contained in the union of these boards centered at lattice points in this set. Naturally, it should contain all the random points in the set I, that's the lambda I. But also, since we have taken a ball around every lattice point, there should be some sort of expansion. We should also count the number of random points in this expansion, and this number should be proportional to the area of to the expanded area, and this should be just the boundary length times r, because we have taken balls of radius r around each lattice point. So the union of these balls has area larger, has increased the area or has expanded the area by r times the boundary length. Now, if we come back to the Hall's marriage lemma, in order for the condition to hold, we need that the difference between the number of random points and the number of lattice points should be bounded by r times the boundary length. And exactly this comes back to the question of what is the growth rate of a gradient lattice animal. There is one caveat because the difference between the lattice points and the random points are not exactly Gaussian processes, but this is just a minor technical point and this can be dealt easily. Maybe the details are not completely clear, but I hope at least I conveyed much of the intuition, or at least some of the intuition, why through Hall's marriage lemma, these two things, the matching and the gradient lattice animal is closely related to each other. Okay. Now, I have what, 3 minutes or?
You still have 10 minutes.
Oh, I still have 10. Okay, yeah. Great. So I can use some time to, as I promised, to sketch the heuristic computation, which suggests the emergence of the fourth order exponent. And this would be the easiest to do in the context of gradient lattice animal, because we only have ID Gaussian variables, and we want to then we just want to find the Grady connected subset in the lattice. The first lesson we learned, which should be fairly straightforward in retrospect, but it took us quite some time to realize, is that in this case, L2 distance is much nicer to work with than L1 distance. Even though in the case of lattice, the sides of the boundary, it's more or less the L1 distance, or it's like the length of the lattice path. But that's not a very nice thing to work with, because the L1 distance does not have the invariance property. L2 is much nicer, and we can first control L2 and then convert it to L1 where we lose a constant factor. That's fine. Also, the second lesson we have learned is that triangles play an important role in all these cases, and I will elaborate this point very soon. The actual proof for lattice animal and for Liouville quantum gravity, which I mentioned half an hour ago, these are quite different, but the underlying intuition is the same, especially the underlying geometric construction is the same. Okay, now let's sketch the lower bound for the gradient lattice animal. The lower bound is, okay, in order to prove the lower bound, basically we want to show that if n is larger than e to this c to the times epsilon to the minus 4/3, then there exists a random animal A star such that the expected Gaussian volume is larger than the expected size of this box. Then we are done. Since we want to use L2 distance other than L1 distance, we can pass to the continuum. So we replace the ID Gaussian variables on the lattice by a standard white noise. And our goal is now changed to construct a random polygon within a box of size n, so that the expectation of epsilon times the white noise value is larger than the expectation of the length for the boundary of the polygon. And this is done via basically a gradient algorithm, which is a local search algorithm, where we recursively expand our polygon. We start with a box. We started with a square, and then we want to expand this. We want to do expansion in the recursive manner, which is also optimal locally, as I will explain now. So let me explain step one carefully, and then the other steps are just similar. So what we do is we place isolated triangles with base S/2. Let's suppose that S is the length for each side currently, and also the height of this triangle is epsilon to the power of 2/3 times S/4 on each side. I clearly should explain the choice of the parameters, especially the choice on the power of 2/3 for epsilon, because this is responsible for the emergence of 4/3. Why do we choose this? Because if we do this by a very straightforward computation, after we add the triangle into the polygon, the increment of the boundary length has order epsilon to the power of 4/3 times S. This is very straightforward. One can just compute it. Also, the standard deviation for the white noise value in this triangle, it's just the square root of the area of the triangle, and we can compute that this is epsilon to the power of 4/3 times S. So the choice of the height here is to ensure that these two competing factors are comparable to each other. This is very standard in optimization. When we have two fighting forces in the optimization, we want to balance them. Okay, and then what we do next is very natural. We just check these triangles one by one, and we add it to the polygon if its white noise value is larger than the increment to the boundary length, because in that case we gain. And after we've done one round, we just repeat. We place triangles on the sides of on each side of the new polygon, and we do the similar type. With this recursion. Initially, since the white noise value has been 0, it contributes nothing to the average. We have a negative value from the length of the boundary. And every round, since we have placed, every round for each triangle, the probability we add it to the polygon is positive. It's like a constant. And once we add it, the average gain is like epsilon to the power of 4/3 times the side length of the polygon. But since we have placed a triangle on each side of the polygon, overall, what we expect to gain is a small constant times epsilon to the power of 4/3 times the boundary length. Now, if n is larger than e to the c times epsilon to the minus 4/3, we can run this procedure for a large constant times epsilon to the minus 4/3 rounds. That's because we have to stop once the triangle had sides 1, and the sides of the triangle shrank geometrically. So this easily gave us the number of rounds we can do this procedure. Then if the large constant c is large enough, we see that after this many rounds, on average, what we gain from the white noise beats the boundary length. I have cheated a little bit in this sketch, like the possible correlation about the triangles we add in different steps in different rounds, but those can be fixed easily, and one can make this argument rigorous. The much harder part is the upper bound on the greedy lattice animal. It required substantially more effort. As I have mentioned earlier, Talagrand proved it via majorizing measure. Basically, this is there is a very basic idea of chaining originated from Kolmogorov in order to bound the supreme of a random process. The idea is very simple, but how to implement it in the optimal way is far from being obvious. And this sort of scheme has been developed by Dadlali and Fanig, and in the end, Talagrand pushed it to the essentially optimal by establishing majorized measure theory, where he defined, in the context of a Gaussian process, Talagrand defined some sort of gamma-2 functional associated with a metric of this process, and this gamma-2 functional captures the supreme of the Gaussian process up to constant. This gamma-2 functional is usually difficult to compute for complicated examples, and for the greedy lattice animal process at hand, we thought initially this would be very difficult to compute. That's why we tried to prove it without explicitly using majorized measure theory. But it turns out, in fact, Talagrand managed to compute it. This computation is also not easy. It took quite some effort using this. It took quite some effort of Talagrand. It also took us quite of some effort using a slightly different approach to prove this upper bound. Our approach is more following the lines of this geometric construction I presented, but Talagrand's proof seems, at least this geometric type of consideration is not explicit, but it's the emergence of the fourth exponent is hiding in some, okay, it's getting a bit technical, it's hiding in some sort of two different gamma-2 functionals, and somehow it appears. I didn't quite see it. At least I couldn't see it in the way that I presented using this geometric construction here. Finally, let me explain why triangles was so important, because this construction we presented looks very much like the cross-graining method that has been widely applied in statistical physics, where the basic idea is one treats a box as a single lattice point and one can do some sort of renormalization. So with this idea, perhaps one think adding rectangles or squares would be more natural than adding triangles. But that turns out to be suboptimal, because if we add rectangles with the same area, then the increment to the boundary length is much larger. And if one do the optimization, one see that in this way, one can only get a square root log n growth on the greedy lattice animal, which would correspond to a Gaussian scaling for the correlation length. Okay, I think I have used up all my time, and probably I will just stop here. Thank you for your attention.
Thank you very much, Jian, for this beautiful talk. I now leave the floor to the audience for questions.
Thanks.
So actually, I think I have one. So the algorithm you presented in this greedy lattice animal, it's for studying correlation length at zero temperature, right?
Correct.
And could you comment on somehow, about positive temperature? How would that adapt to that case?
Yeah. Yeah, sure. Actually, the temperature is not the key difference here. The moving from gradient lattice animal to the random field Ising measure, there is substantial difficulty, because for the gradient lattice animal, we consider white noise, right? There is spatial independence naturally. Mm-hmm. That gives us a lot. You need this in the recursive construction. But when we consider an Ising model, then the Ising spins correlated in some complicated way, and this is very difficult to control. Mm-hmm. In this case, I think there are two ways to control the correlation. One is to show that the absolute value of the correlation is small. Two is to show that even though there is correlation, but it's in your favor, it's in the direction that you favor. Mm-hmm. And in this case, we choose the second direction. We somehow we build our construction in a more careful manner, so that even though there's correlation, but it's the direction is in the direction is in the way that you want, and this solves the problem. I cannot explain the details I cannot explain the details of this without more slides. But that's the idea. We do not control the absolute value of the error. Either we say that the error is it's only helping us.
I see. Yeah.
This has to use the monotonicity of Ising model. That's why we cannot quite do this for Potts model, in case that's what Michael is wondering.
Mm-hmm. Thank you. So I see a question from Michael Eisenman.
Oh, well, thank you for a beautiful lecture and for injecting such cool ideas to the subject.
Thanks,
two questions. One is, I presume that in appending those triangles, you could have also subtracted them. Am I right? And then generate kind of a fractal curves which swings in both directions.
You mean instead of adding it, you want to subtract triangles?
Yeah.
Yeah, that should be the same, I suppose. I just feel adding is more natural. Yeah.
Yeah. Okay. Just and the other is, I mean, what I meant is to do both, in the sense that the curve actually may be, you may generate curves which are winding in both directions.
I see.
Slightly. The wind is not very strong here. It's a bit of fractal decoration, if I understand correctly. The other is, do you have the 4/3 bound both for upper and lower bounds?
Yeah, we have the lower bounds for very low temperatures. But you can imagine that at high temperature, this wouldn't make sense, right? Because we know there should be exponential decay. Yeah. We don't know until which temperature this 4/3 scaling holds. This is out of reach at the moment.
But I'm confused. The analysis is of the rate of exponential decay, right? Not of whether there's exponential decay or not, but the correlation length, behavior of the correlation.
Sure. Oh, okay. Maybe I should be more careful. At high temperature, there is exponential decay on the long range order, and the rate of the exponential decay is a constant. It does not shrink as epsilon goes to 0.
Oh, I see. So it's on epsilon dependence of what is
right. Yeah. That's because. Yeah. Go ahead.
And do you get the power law for both upper and lower bounds, or just one-sided inequalities?
You mean the 4/3 power law?
Yeah, the 4/3 power law.
Yeah, we do get it for both upper and lower bounds, but again, this is for very small t.
Yeah, okay, very nice. Thank you.
Yeah, thanks.
Thank you.
So I see another question from John Imbri.
Yeah, hi. Thanks very much for a beautiful presentation. I was just trying to clarify this, pretty much the last point you made about basically the L2 versus L1 distance. I mean, when you bump up these triangles, the perimeter goes like the square. I understand that, but somehow when you go all the way down to the the original lattice scale, all of a sudden it no longer looks Euclidean, it looks like the L1 distance. So I don't quite understand how you get the square out of it.
Well, that's because you try to, we think of L2 distance all the way until the very end, we convert the L2 to L1. At the very end, we can convert L2 to L1, you lose a multiplicative constant, right? That you can do. But we don't do this for every step. What you have imagined is every time in every step you convert L2 to L1, of course, then this would give too much error. But we just keep track of L2 distance throughout these recursions, and only at the very last step, we convert the L2 to L1, so we lose a multiplicative constant factor for the boundary length.
Okay, but maybe what's confusing me is that no matter how you do it, when you descend to the lattice, there simply is no path from A to B that that has the L2 distance. It's the L1 distance. So the number of steps in each direction are pretty much the same.
The number of steps, I'm not quite sure what you meant. There is some approximation you need to do when you turn this white noise to a lattice field, but this error can be controlled. I don't know whether.
Okay, well, I better. I'll put my thinking cap on, I guess. Thanks again for a great talk.
Sorry, maybe it's a bit too late for me to be able to answer your question. Yeah, but there is some error in the end, but this you can compare it in the end. I mean,
okay, thanks a lot.
Okay, thanks.
Are
there other questions?
Yes. So probably I missed something because this is very late for me too. But so we saw the connection to this greedy lattice animal, but what about this Liouville quantum gravity? How did you show us the connection with animals or anything like that?
Well, okay, that's a good question. The connection between LQG to greedy lattice animal is not as transparent. I showed you a mathematical connection between random field Ising and greedy lattice animal, right? This connection between LQG and the others is via this geometric recursive construction I presented to you. What happens is there is a very similar recursive argument that give you the fourth exponent in the LQG exponent. But I cannot say mathematically that a priori we can relate this together. That we are unable to do. It's just this heuristic computation shares the very similar philosophy. But all of this is sort of in retrospect. We didn't know this. I first worked with Subhajit on the LQG, but for quite a while, we didn't know that that kind of computation would be useful for the random field Ising. Also, what I didn't tell you is for greedy lattice animal, we have both upper and lower bounds. But for the LQG, currently we only have the one side bound. The other side, we're still working on it. And actually, it's much harder than.
But you still, but you believe that this fourth order exponent behavior is the correct behavior for the gamma?
We do believe so. We do believe so. But yeah, but these things are delicate. Until we actually have a proof, I wouldn't want to. Yeah, I can only say that's my best guess. I think that should be the case, yes, but we don't have a proof yet.
Thank you. Yeah, it was a beautiful talk.
Other questions or comments? Does not seem to be the case. So let's thank Jian again for the beautiful talk and for the discussion.
Thank you so much.
We now stop the recording.